Hello and welcome back to Calculus1. We are talking about derivatives of trigonometric functions, which is a very short section because we are going to have 6 shortcut formulas to find the derivative of these trig functions. Now, in a perfect world, you would memorize the 3 and then the other 3 are symmetric, and we'll see what that means. But let's first see what it takes, right, to do the derivative using the standard derivative definition. So on exam 2, so not the one that is coming up in 2 days, but the exam 2, which will be whatever month later, on that exam, you might have a question that says, what is the definition of the derivative? In which case you have to write f prime of x is equal to limit h goes to 0, and then you have your f of x plus h minus f of x over h. So this was your definition of the derivative that was given in 3.1. And this is supposed to be used to find all derivatives. And then derivatives lead to the slope of the tangent line. You can measure the change, and then you give birth to all of the physics and engineering and chemistry and technically everything that has any kind of science attached to it, including economics, as you will see later, and so on, business. Now, if you are supposed to take the derivative of sine x, well, you use the definition above. You write limit h goes to 0, and then you have your sine of x plus h minus sine x over h. And now you are done with your calculus part. This is where algebra, and or if you want to call it trig, pre-calc, takes over for you to solve this limit, right? So you copy the limit. That is one of the very important skills for your first exam, even though this is not the review now, but I'm just going to say it anyway, because I'm sick and tired of taking those points where they really don't need to be taken off. Copy this in every step so you don't forget it at the end. A lot of students do all of the calculations correctly and they never take the limit at the end because they forgot that there was a limit, because in a test 10 steps before that they didn't write it. Your brain remembered that there is no limit, and that's why you didn't take it at the end and the problem was wrong. So when you have a limit problem, write that limit in every step until you use it in the last step. All right, so now we're taking the limit. This over here is basic chapter 2 problem. That's it. This is a chapter 2 problem, and you are supposed to solve this. Now, the only thing you can do here is to use that sign of, I think your class could have x plus y or alpha plus beta or a plus b, whatever. So you are supposed to use the sine of sum of two angles, and that is sine of the first, cosine of the second, plus cosine of the first, sine of the second, and then we have minus sine x, and everything is divided by h. So all I did here is use that basic identity of addition of two angles to break it apart. Here is copying the limit again so I don't forget it. And now we realize that this term and this term both have sine x. So we factor that sine x, leaving cosine h minus 1. And now break it into a separate function. Actually, you know what? Let's do that next step. Plus cosine x sine h. There we go. Now, what you see over here is that you have fraction that has two terms. And we know from the rules of limits from chapter 2 that we can write this as a two separate limits. So limit h goes to 0 of sine x cosine h minus 1 over h, plus another limit, right, that was the rule, of cosine x sine h over h. So we are able to split the limits. If we have separate terms, we can give limit to each one of the terms. And because they were fractions, each one gets the common denominator over h. Once we have that, we now need to solve these two separate limits. And both of these have a function that has a variable which is not in the limit, which means in the eyes of the limit, which is in terms of h, this is a constant. In the eyes of the limit, sine x is a constant because the limit h goes to 0, not x goes to 0. H goes to 0. So any variable x is just a constant in the eyes of the limit that has h going to 0. So we can kick sine x outside, which is another limit rule, leaving us with cosine h minus 1 over h. And over here the same rule applies. The cosine x is constant in respect to variable h. So limit h goes to 0 is sine h over h, which is what we have there. Now, in the book, they tell you these are the special limits, memorize this, but you are going to learn how to do these limits in chapter 4 anyway. So right now we can skip those unpleasantries, right, and realize that this one is going to 0 and this one is going to 1 because we looked into the book and, you know, or it came to you in a dream, whatever. Those limits are equal to that, and you will know why when we reach, I would think it's 4.7 or 4.8, whatever. But whenever we do L'Hopital's rule, you will be able to solve these limits instantaneously. So you have your sine x times 0 plus cosine x times 1 for a total of cosine x. And there you have it. The derivative of sine x is cosine x. So this was all this work to figure out this shortcut formula which you are supposed to memorize so that you do not have to go through this calculation every time you need to take the derivative of sine, which will be a lot. Now, you see what we had to go through, right? Especially with this identity and factoring. And you can pretty much do the same. The identity would look a little bit different, but the same steps. To solve d dx of cosine x is negative sine x, which would be the next formula which you can memorize. So derivative of sine is cosine, derivative of cosine is negative sine. Perfect. We are done with the introductory talk, and we also discovered 2 out of 6 formulas. The next one that we want to learn about is the derivative of tangent. So how would you approach derivative of tangent if you want to compute it? You have 2 options. Easy and hell on earth. Let's see which one you guess first.
Would it be cotangent x?
Nope. I'm not trying to ask you to guess the solution. I'm trying to see what would be the step or the way to compute this. We will calculate the answer.
You would replace tan x with sine x over cosine x.
And then do what? That's perfect.
The quotient rule?
Quotient rule, yes.
Yeah, quotient rule.
Yes. All right, so you guys know quotient rule from last class or 2 classes ago, whatever. So you can apply quotient rule to this. So we don't have to go with the tangent of x plus h minus tangent x, like that would be insane. It's very easy to use the quotient rule actually. So, all right, let's, I'm going to give you a few minutes to try and compute this on your own so you can practice your basic trig. All right, 5 seconds left. So hopefully you wrote down cosine squared in denominator, then you have your cosine x. Derivative of sine, we said it's cosine x and then minus, then copy the sine x, and the derivative of cosine is negative sine x. So a little bit of this basic algebra over here. You have your cosine squared x plus sine squared x, and the denominator is cosine squared x. From this point, you have two ways to deal with this. You can say this is equal to 1, which is 1 over cosine squared x, which is secant squared x, right, in a basic identity. Or you can break this into cosine squared x over cosine squared x plus sine squared x over cosine squared x, and get your 1 plus tangent squared x, which is again Pythagorean identity basic equation, basic identity, I mean, into secant squared x. Either way you deal with this is going to be the derivative of tangent x is secant squared x. Ta-da! There it is. All right, one more, and it's going to be the same deal. What is the derivative of secant x? How would you approach this one? Anyone awake? What is secant equal to? I have 20 of you on Zoom and no one is talking. Come on, guys. Wake up. We have to... Aha. YouTube chat is kicking in and saving the day. So you can go back and go back to sleep. Yes, you're correct. YouTube chat, right? We have the derivative of 1 over cosine x. And go ahead, do the quotient rule again. So I'll give you again 2 minutes or so. Now it's even easier because the numerator is 1, so that should quickly reduce the work.
I'm sorry, Professor. I don't know where to start.
Just do the quotient rule. This is a quotient, right?
Yeah.
Yeah, do the quotient rule formula. Same like previous problem. Fill in the quotient rule and then simplify algebra. So let's see. Again, cosine squared down there, cosine x here, derivative of 1 is 0, minus cos p1, and derivative of sine, derivative of cosine is negative sine. So that was the quick quotient rule formula. So the first term goes to 0, so all we get is sine x over cosine squared x, which we break down into 1 over cosine x, and then sine x over cosine x, because cosine times cosine is cosine squared, and we can have 1 times sine in the numerator, which works out to be secant x tangent x, and that's another formula that we can memorize. Derivative of secant x is secant x tangent x. So now you know how to obtain all 6 formulas. The first 2, you can use the definition for sine and cosine. You can use the definition to work out the derivative. And for the last 4 functions, which are tangent, cotangent, secant, and cosecant, for those 4 functions, you get to use quotient rule, right? Because you can rewrite those 4, and you have everything done. So now, let's write all 6 derivatives in one spot and see what is the easy way to memorize all of them, and how much actually you have, how much effort you need to put into remembering all of these things. So, we go with the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. Now, we haven't done all of these. I only did 3 out of 6 and gave you the cosine, right? So you will have to trust me on the last 2, and then you can go and verify them because you know what calculations you're supposed to use. The derivative of tangent is secant squared x, and the derivative of cotangent x is negative cosecant squared x. The derivative of secant x is secant x tangent x, and finally the derivative of cosecant x is negative cosecant x cotangent x. There they are. 6 trigonometric functions with their derivatives. This will be used a lot later on, not just in Calc 1, but going on to Calc 2 for integration by parts, trigonometric integral, trigonometric substitution, and so on. It will be used a lot. There will be integral tests within series, in the series section, chapter. So a lot of situations when you will be using derivatives of this. Oh, chapter 12 is all about trig. So yeah, there's that one. So you will have a lot of opportunity to show off your math skills. Now let's see. What kind of symmetries / similarities, if you like that word better, you can spot with these equations that could potentially help you remember all remember all 6 of them. Do you see any patterns, anything that at all? Just say it / type it. Okay, the chat is catching on to similarities. I am yet to hear anyone speak about, guys, are there obvious things that you can say? You know, single sine, single cosine on the first line, then a single tangent, single cotangent, and then the squares over here. How about the fact that all of these are negative? I mean, these are the things that you are observing just by looking at. How are you alive? Like, you notice the pattern that if you are not crossing the street while car is there, right? You stay alive. These are the things that, you know, I'm really concerned that I asked this question, what, 2-3 minutes ago, and no one said anything. 22 people in their 20s or older are looking at these formulas, and I'm asking for patterns. And they're so obvious that the way I wrote them in each line, right? You have sine linked to cosine, which was hinted on the YouTube chat thing. So we have the pairing. You see that sine and cosine are always a pair. You also see that all formulas are only tangent secant and cotangent cosecant. You will never find different pairs. You will never find tangent with cosine or cosecant with sine. All of the pairing is strictly sines with cosines, secants with tangents, and cosecants with cotangents. And then per row, each form is the same. And all of the cos, cosine, cotangent, cosecant, so all of the cos are negative, where the other ones are positive. So it's sufficient to remember these three, and these are immediately by symmetry given because they look absolutely the same. You switch tangent with the cotangent and then secant with the cosecant, and it's negative because it's a co, right? You swap secant with the cosecant, look, secant with cosecant, tangent with cotangent, and then you have a negative again because it was a cosecant. So a lot of symmetry here, and it's very, very easy to memorize all of these formulas and have them ready for your derivatives later on. And as I said, it will be a lot of those, especially those going into mechanical, electrical, chemical. You will see a lot of this stuff in your later coursework. So those are the derivatives. And now useful formulas to know. So I'm just going to say trig review over here. So this is the bare minimum of formulas that you need to know to survive in Calc 1. And then, you know, Calc 2 will bring other stuff. But for now, what you need for this section is obviously sine squared x plus cosine squared x equals 1. And the variance for secant and tangent. So 1 plus tangent squared x is secant squared x, and 1 plus cotangent squared x is equal to cosecant squared x. Observe that the Pythagorean identities over here also follow the same pairing you guys have in calculus. Sines only with cosines, tangents only with secants, and cotangents only with cosecants. You also need sine 2x is 2 sine x cosine x, and obviously cosine 2x is cosine squared x minus sine squared x. Tangent is not that important because you can literally write, you know, division of these if you need it, but rarely you do. And then I will add to this list of basic trig stuff when we get to chapter 4 and we need equations, and then when we get to chapter 5 and we need the power reducing formulas, I will add those to the trig review. But now to survive, I didn't write tangent x is sine x over cosine x. Cotangent x is either 1 over tangent or cosine x over sine x. I forgot about the basic, there we go, equations over here. So just in case that someone missed these are the, not sine, cosecant, oops. Cosecant x, and then sine x goes here. There we go. So this is your trig review. Let's put in a green box, I guess. And these are the formulas that you will probably run into as you do your homework, especially the double angle one. That's allows you to simplify a lot, and then sometimes these formulas are useful to to swap the pairs, because you can't really do pairing very well if you have different functions that don't work. So those are the only links between the two worlds. So now what kind of problems are we expecting? Well, mainly product rule, quotient rule problems until we learn function composition and what we call chain rule. So now, well, your problems are like this. Find the derivative of x squared sine x. What rule do we get to use to find this derivative?
Product rule.
Awesome. So use the product rule, and let's see if you can factor anything. Please make sure you factor so it's simplified as much as possible. The chat came up with the answer, but I am not too enthusiastic because product rule was not used. You have to use the product rule. Copy the first times derivative of the second plus copy the second times derivative of the first, and then go factor and do things. So copy the first times derivative of the second plus copy the second times derivative of the first. So the only thing we can factor here is x, and we're left with x cosine x plus 2 sine x as the factored solution. All right, let's see this problem. What should we use?
Quotient rule.
We can use quotient rule. Okay. Let's see. Secant squared x, secant x, derivative of the top is 2x, minus copy the top, x squared plus 1, times the derivative of secant, and that's secant x tangent x. So now we can kick secant x out, which leaves us with 2x minus x squared plus 1 tangent x divided by secant x times secant x, because we separate that so we can cancel one. I mean, I could have canceled in the square, but whatever. And there it is. We have 2x minus x squared plus 1 times tangent x divided by secant x, and that would be a wrap. Or, ready? Or d dx is equal to x squared plus 1 times cosine x. And now you can do product rule instead of quotient. And you have to come up with the same answer. Copy the first, derivative of the second, plus copy the second, times derivative of the first, which is 2x. So what this equals to? It equals 2x cosine x minus x squared plus 1 sine x. There we go. If you multiply this over here by secant x over secant x, you will get this form. I can show that even though it's a basic pre-calc. So if I do 2x minus x squared plus 1 times tangent x, now remember tangent x is sine over cosine. So let's write that in, sine x over cosine x. And this secant in denominator is 1 over cosine x. So if you multiply top and bottom by cosine x to cancel, you get this immediately. Because in the denominator, it cancels. And on the numerator, it distributes on both terms while it cancels in the second one. So you will have 2x cosine x minus x squared plus 1, and then cosine and cosine cancel, and you just have sine x, which is exactly the same as the blue. Now, product rule is always better than the quotient rule because it's less calculations, no fractions, less algebra, less everything. So if you are able to, weasel your way out of quotient rule, it's highly suggested, right? You do that if you can weasel out. So there are two ways to do the same problem. I was able to convert the problem using basic trig identity that 1 over secant is cosine, and that changed the whole story and made it much easier. Now, if the problem was flipped, then the blue would not be possible because once you have x squared plus 1 in denominator, that cannot be magically transported up. I mean, you can write x squared plus 1 in parentheses raised to -1, right? And make it a product rule. But it introduces a whole new method of derivatives which we haven't learned yet. We are going to learn that on Monday. So that's it for trig. It was dragged out a little bit. Usually I like to keep this under 35 minutes, but we did extra examples and discussion. Well, actually, discussion, haha. I will be back with 3.5 soon. Time to take a few minutes break.